This is SpaceTime, Series 19, Episode 89, for broadcast on the 14th of December 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, looking at the ultimate fate of planet Earth. New clues about the creation of Jupiter, the solar system's king of planets. And Japan to test a new way of cleaning up space junk. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have had a chance to peer into the future and see what our home planet the Earth will be like in 5 billion years' time. In order to look into the future, the authors observed an aging red giant star, 100 times bigger than the Sun, called L2 Puppis, which is located just 208 light-years away, relatively nearby in cosmic terms. 5 billion years ago, L2 Puppis was almost identical to the Sun today, in terms of its mass, luminosity, and its age. And just like L2 Puppis did, our Sun is now slowly burning through its nuclear fuel supply. And again, like L2 Puppis, the Sun will also experience an intense mass loss through a very strong stellar wind. Its outer gaseous envelope will continue to cool and expand, eventually becoming so bloated it literally floats off as a planetary nebula. The end product of the Sun's evolution in, say, 7 billion years from now will be a tiny white dwarf star, the slowly cooling stellar core of the Sun, a sphere of oxygen and carbon about the size of the Earth, but super dense, with just a teaspoon of white dwarf star material weighing well over 5 tons. Now, as you'd expect, this metamorphosis will have a dramatic impact on the planets of our solar system. For a start, Mercury and Venus will be engulfed by the red giant and destroyed, but the fate of the Earth is still somewhat uncertain. Now, over the next billion years or so, as the Sun gets bigger and brighter, the Earth's seas will evaporate away and all life on this planet will be destroyed. Earth's atmosphere, as well as probably its crust and mantle, will be blown away. But what of the Earth's core? Will it survive the red giant phase and continue orbiting the white dwarf star? Or will it also be engulfed and destroyed, like Mercury and Venus, during the red giant phase? To try and answer those questions, astronomers used the Atacama Large Millimetre Submillimetre Array Telescope ALMA to examine L2 Puppis in detail. Located in Chile's high Atacama Desert, ALMA consists of 66 individual movable radio telescope dishes, which together form a giant virtual telescope with a 16-kilometre diameter. Reporting on the pre-press physics website archive.org, the authors were able to confirm that L2 Puppis is now about 10 billion years old, roughly twice the age of the Sun. They also found that while it was once virtually identical to the Sun, it's now lost roughly a third of its mass. And the authors predict the same thing will happen to our Sun in the future. Just as intriguing, the authors also detected an object orbiting the red giant roughly about 300 million kilometres out, which is about twice the distance between the Sun and the Earth. A deeper understanding of the interactions between L2 Puppis and this planet will yield valuable information on the final evolution of the Sun, as well as its impact on the Earth and other planets in our solar system. Whether the Earth, or at least part of it, will survive the Sun or be destroyed is still uncertain. And L2 Puppis may well be the key to answering that question. You're listening to SpaceTime. I'm Stuart Gary. A new study has concluded that Jupiter probably reached its present-day size as the solar system's largest planet within just 5 million years of the very first solid material condensing out of the primordial gas. The findings, reported in the journal Science Advances, claims a specific class of meteorites known as CB chondrites has offered scientists new clues about exactly when the planet Jupiter took shape and began wandering through the solar system. Scientists have long theorized that Jupiter probably did not form in its current orbit, which is about 5 times further away from the Sun than the Earth. The idea of a Jovian migration explains a lot about the way the solar system looks today, including, for example, why Mars is so much smaller than planetary accretion models predict. Under this hypothesis, Jupiter once orbited much closer to the Sun than it does now, during which time it would have swept up a lot of the material needed to create a larger Mars. But while most scientists agree that the giant planets probably did migrate, the exact timing of Jupiter's formation and migration has been somewhat of a mystery. And that's where these meteorites come in. CB chondrites were formed in the early solar system, most likely in the present-day main asteroid belt, as objects slammed into each other with incredible speed. This new study uses computer simulations to show how Jupiter's immense gravity would have provided the right conditions for these hypervelocity impacts to occur. That in turn suggests that Jupiter was near its current size and sitting somewhere near where the main asteroid belt between Mars and Jupiter now exists when the CB chondrites were formed, which is about 5 million years after the solar system's first solids condensed some 4.6 billion years ago. The computer models show that Jupiter's migration would have stirred up the asteroid belt sufficiently in order to produce the high impact velocities needed for CB chondrites to form. The study's lead author, Brandon Johnson from Brown University, says these meteorites represent the very first time that the solar system felt the awesome power of Jupiter, the king of planets. Chondrites are meteorites comprising tiny spheres of previously molten material called chondrules. They're among the most common type of meteorites found on Earth. However, CB chondrites are a rare subtype which all date back to a very narrow window of time, roughly 5 million years after the first solid material condensed out in the early solar system. Johnson says while chondrules in other meteorites give a range of different ages, those in CB chondrites all date back to the same brief time window. And he says CB chondrites are also significant because they contain metallic grains which appear to have condensed directly out of vaporized iron. Now that's important because vaporizing iron requires extremely high temperatures, which means extremely high velocity impact of at least 20 kilometers per second. The problem is traditional computer models of the early solar system only produce impact speeds of around 12 kilometers per second at the time when the CB chondrules were formed. So Johnson worked with Kevin Walsh from the Southwest Research Institute in Boulder, Colorado, to generate new computer models of the chondrule forming period, which includes the presence of Jupiter near the present-day position of the main asteroid belt. And that's significant because big planets generate heaps of gravity, and that gravity can then be used to slingshot nearby objects at high speeds. NASA often takes advantage of this dynamic gravity assist process to fling spacecraft around planets in order to generate increased velocity. As part of their model, Walsh and Johnson included the Grand Tack scenario for the formation and migration of Jupiter. The Grand Tack scenario is the most promising of all the nice planetary migration scenarios around at the moment. It suggests Jupiter actually formed somewhere in the outer solar system. And as it accreted its thick atmosphere, it changed the distribution of mass in the gassy solar nebula surrounding it. And that change in mass density caused the planet to migrate inwards towards the Sun to about where the main asteroid belt is today. Later, the formation of Saturn created a gravitational tug which pulled both Jupiter and Saturn out to where they are now. Walsh says including the Grand Tack in their model at the time when the CB chondrites were formed results in a huge spike in impact velocities in the main asteroid belt. In fact, the speeds generated in this model are easily fast enough to explain the vaporized iron in CB chondrites. The most extreme collision in this model involved an object with a 90 kilometre wide diameter slamming into a 300 kilometre wide body at a speed of around 33 kilometres per second. Now, such a collision would have vaporized around 30 to 60% of the larger body's iron core, providing ample material for CB chondrites. The models also show that the increase in impact velocities would have been fairly short-lived, only lasting for about 500,000 years or so, literally the blink of an eye in cosmic terms. Now, this short time period allows the researchers to conclude that Jupiter must have formed and migrated at roughly the same time that the CB chondrites were being formed. Now, the authors admit that while the study is strong evidence for the Grand Tack migration scenario, it doesn't necessarily preclude other migration hypotheses. For example, it is possible that Jupiter formed closer into the Sun and then migrated outwards rather than the in and then out migration of the Grand Tack. And that's got its own problems in terms of the sort of temperatures and environments in which gas giants like Jupiter can form. Still, whatever the scenario, the study does provide strong constraints on the timing of Jupiter's presence in the inner solar system. Johnson says it seems obvious to him that you'd really need something like Jupiter in order to stir the asteroid belt up that much. The Grand-Tack hypothesis also allows the inward migration of Jupiter to fling objects from the asteroid belt into the outer solar system, while the outward migration of Jupiter and Saturn both work to fling asteroid belt objects towards the inner solar system, causing what astronomers call the late heavy bombardment, and also causing the ice giants Uranus and Neptune to move further outwards, and possibly even changing their orbital places in the process. The orbital dynamics of this could have also resulted in a third ice giant existing, which would have been flung to either a more distant yet to be discovered location in the Kuiper belt, possibly our missing planet 9, or alternatively flung out of the solar system completely and into interstellar space, where it now wanders as a rogue planet. I'm Stuart Gary. This is SpaceTime. The January issue of Australian Sky and Telescope magazine has hit the newsstands. Joining us now with the details is the magazine's editor, Jonathan Nally.
All right, so this month we take a look at the Dawn mission, which I know you've spoken about on the show many times. This is the one that's gone to two of the large bodies in the asteroid belt between Mars and Jupiter, and in particular the dwarf planet Ceres. Now, Ceres, of course, used to be considered the largest asteroid, but with the reclassification of solar system bodies, it's now considered a dwarf planet, just as Pluto is, although not everyone, yours truly included, completely goes along with that, but that's for another time. Then let's not get into that. I think we've spoken about this before. Now, Ceres is a really interesting place because it's large enough to form it into a globe, into a round ball, like a normal planet, if you like. That's
one of the definitions, self-gravitation, yeah.
Yeah, one of the definitions of these dwarf planet things. So it's a really large body. But one of the really interesting things about Ceres is that it has this large crater with this bright spot right in the middle of it. And this had been spotted a long way out when the Dawn mission was still a long way out. In fact, even the Hubble telescope spotted beforehand there was some sort of bright patch in Ceres, and no one knew what it was.
Yeah, it looked really freaky.
Yeah, was it ice? What was it? What was an alien civilization?
Alien looking at us, yeah.
Yeah, exactly. So what was it going to be? So we had to wait until the Dawn mission got right up close to have a look. And what it just seems to be is basically salt deposits of various kinds in the middle of this crater. In fact, there are about 130 of these bright patches all over the globe of Ceres. And yeah, they think they're probably salt deposits, possibly formed from some sort of briny liquid that might have seeped up from below, possibly heated up when asteroids and meteoroids and things smashed into the surface and, caused a bit of heat. And this ice underneath the ground melted and sort of trickled up, bringing salts with it. And that raises the point, of course, that they think that Ceres, although it's mostly rock, is actually made up of about 25% water in the form of underground ice. So this Dawn mission is actually really quite handy going around this dwarf planet Ceres because they're getting a good look at a body that's got a lot of ice underneath it. There are other places in the solar system, other moons of Jupiter and Saturn, and you've got Pluto itself and all sorts of other bodies that are either made of ice almost completely or they think they've got ice or water underneath the surface. But we haven't really had any spacecraft in orbit around those other worlds, but we've got Dawn in orbit around Ceres, so it's in the right spot at the right time. So we've got a really good, interesting feature about that written by the scientists who are involved.
And the great thing about the Dawn mission, it didn't just go to Ceres, it also went to Vesta. So between Vesta and Ceres, you've got two completely different types of asteroids, one on each side of where water solidifies the snow in space, the snow line. And so it's provided so much fascinating science. And it continues.
It has, yeah. Look, and the great thing about, as you say, it's been to two bodies in the asteroid belt. It's the first spacecraft, in fact, that has gone into orbit around one body and then blasted out of that orbit and gone off to another one and gone into orbit around that. So it's been orbiting around Ceres for quite a while. And look, it still has fuel left. It's got one of these xenon thrusters. It's not like a normal rocket engine. It's got a xenon thruster which produces, it's like an electric rocket, if you like. Gives it a simple explanation. And very low thrust, but continuous thrust, and it can go for long periods of time. And now, having completed its primary mission at Ceres, some people have tried to convince NASA that, hey, we've still got fuel left, why don't we go off and have a look at another asteroid again? And it could certainly do that, but NASA has said, no, yeah, while we could do that, that other asteroid you're proposing is not that exciting. We're actually better off staying here at Ceres, which is this amazing big round world with all sorts of geology and stuff going on and all this water ice underneath, presumably, and fascinating things to learn. Let's stay here and just keep studying this one. one. So, a very good value mission, Dawn mission. Now, also in the January issue of Australian Sky and Telescope, we've got a really interesting story about amateur astronomers taking the deepest image ever taken by amateur astronomers. Now, what do I mean by deep? It's like looking into the water. The deeper and deeper you look, the further and further you're looking down into the water. It's the same thing when astronomers are looking out into space. They say as you're looking deeper and deeper, it means looking further and further out into space. And the further and further you look, the things are further away, and therefore they appear to be fainter, therefore they're harder to photograph. So there's a bit of a challenge on to see who can photograph the furthest, faintest thing. That means the deepest image, if you like. And these amazing people, a team of astronomers, have set up their own observatory in a prime spot in Chile where they've got incredibly clear, dark skies, really good place to do astronomy. And they set up this observatory with all the latest high-tech gear and everything, and they've taken one of these really, really deep shots, and they've got the world record for the deepest shot by an amateur. For the technical people, they've spotted a galaxy that's magnitude 26.4. Now, I remember, back in the 80s when even professional astronomers couldn't get past magnitude 20. That was really on the border of what they could do. And now amateurs are just using off-the-shelf gear you can buy and taking these really, really deep images. It's quite amazing the stuff that amateurs can do these days. It is on a par with what professionals were doing a decade or two ago. It's really amazing.
Well, that's why professionals are getting amateurs to do a lot of their backup research now, because these guys and gals, they love doing this sort of stuff, and if they can get their name in a scientific paper, that's not bad either for a hobby.
Yeah, well, look, professional astronomers have always relied upon amateur astronomers to do some of the work for them, because professional astronomers can only be in one spot at one time, or using one telescope at one time, but you could have a whole team of people all around the world helping you out with their own telescopes and doing their own thing. Now, if you've got cloudy weather, then someone else might have clear weather. So amateurs have been involved with discovering comets and asteroids and supernovae and you name it, and observing the planets.
Atmospheric
meteors.
Layers on Mars, storms on Saturn. Amazing.
It just goes on and on and on. And really, in fact, if you want to go back, centuries ago, or even not that far ago, really, there weren't that many people who would be considered professional astronomers, whose job it was, and they were being paid by someone to do science. You go back into the 19th century and earlier, and you had the concept of what was called the gentleman astronomer, who was someone who was independently wealthy or had a really well-paid job, and their hobby was to do astronomy. And they were the ones who were doing the science, and self-trained. A lot of them set up their own observatories, bought their own gear, and discovered all sorts of things. These days it's different. You've got people who, go to university, get a degree, become an astrophysicist, use all the best gear and the top observatories all around the world, but there's still a place for the amateur astronomer, and the sort of gear that the amateur astronomers can use these days makes their contribution really, really valuable. Now, speaking of which, also in the January issue, we've got our hot products for 2017. We've picked what we think are the best 20 hot products. This includes things like telescopes, special digital cameras for astronomy, software packages, and all sorts of accessories and things that you can get to help make your astronomy a lot more fun and a lot easier, all that sort of thing. So check out the issue for all our list of the 20 top products. There's some really interesting stuff in there, some expensive, some cheap, some easy, some hard, whole range of things for all sorts of different purposes. And also, finally, in the issue, we've got a story on the ExoMars mission, and I know you've covered this on the show, the tragic loss, of course, of the Lambda, which plummeted to the ground on Mars and
it went bang.
It went bang, as you do when you plummet to the ground. But the orbiter, of course, felt like a safe. But the orbiter, of course, is doing great work. It's slowly changing its orbit, and I think it's due to start doing science. So actually quite a while away, towards the end of 2017, before they get the orbit exactly the way they want it to be. And its purpose, of course, is to study Mars, in particular its atmosphere, and in particular to look for signs of the gas methane. Now, methane's really interesting. It's one of these greenhouse gases that we're concerned about here on Earth. It's a gas that's very short-lived. Once it gets into the atmosphere, it doesn't hang around very long. It gets broken up very easily into its constituent bits. So to have methane in the atmosphere means it needs to be sort of continually replenished, otherwise it just goes away. Now, trace amounts of methane have been detected on Mars in the past by other spacecraft.
And also by Earth-based observatories as well. It wasn't just Mars Express detecting them. There are a number of Earth-based observatories which found this stuff there as well. Something's replenishing it.
Well, something's putting methane into the atmosphere of Mars, it seems. Now, there are two ways you can do that. One is through sort of geological processes like volcanoes, that kind of thing. Or the other is it's a byproduct of living organisms like cows and all that sort of stuff.
Martian cows.
Martian cows. But the other thing is that there isn't any evidence of volcanoes on Mars. There's really no evidence of ongoing geology of that kind. There could be something going on underground or something we haven't spotted yet. So the jury is still out as to why there's methane there, how much, where it comes from. There's a hint or a suggestion that it's seasonal, that it comes and goes depending on the temperature during the course of the year. Now, that's a really interesting thing because, what could be happening as the weather warms and it gets cooler again?
Got a bit of meltwater, have bacterial life there of some description, who knows?
Who knows what's going on? So it'll be very interesting to see what
What's your money on?
up.
Are we going to find bacterial life on Mars?
I'm sort of 50-50 with simple life or geological processes, I have to say. No, perhaps more like 30-70 life and 70 geological processes. Either is possible. Either is certainly possible. Whether ExoMars will be the one that helps nail down, and it probably won't be. It's just going to, do broad-scale measurements of where and when this methane is coming from. It'll then be up to other investigations, I suppose, to try and figure out, okay, well, now we know where it's coming from, but what is causing it? I just don't know. We don't know, do we?
It's a great mystery.
It's a really interesting one, and it's one of these really interesting things of science where it's like a telltale or a clue or evidence in a detective novel. We've got this evidence for this, and as far as we know, it can be caused by that or this. Which one's it going to be?
Where's Hercule Poirot when you need him?
It's a bit like that, So
I keep thinking back to Alan Hill's 1989, that meteorite which had fossilized crystals in it, and they still don't really know what those fossilized crystals really are.
They don't, and there was a big fanfare about that, wasn't there? Of have we found life on Mars? Bill Clinton had the press conference a whole lot. Yeah. And
it took everyone's attention off that blue dress.
And it sort of all died away a little bit, hasn't it? In fact, I was just thinking today also of a couple of other things in science that have been similar, I suppose. One was the announcement a few years ago. Press conference was held with NASA. Some scientists reckon that they'd found some life on Earth in a lake that's full of arsenic, I think it was.
Oh yes,
that used arsenic and incorporated in its DNA.
Yeah, very famous Australian researcher involved in that too.
Well, there was a lot of famous research going on in there, and of course, a big fuss. But of course, it was instantly savaged by the rest of the scientific community, and they just tore that research apart, and basically no one believes it anymore. So you've got to be careful what you do. And of course, going all the way back to the 1980s and Pons and Fleischmann and cold fusion.
Oh,
cold
fusion, yes.
Good old cold fusion. So you've got to be. We know how science works. It plods along.
Extraordinary claims require extraordinary proof.
Yeah, you be very careful with your claims before you got all your evidence and you got all your ducks in a row. So with this methane, we just don't know. It could be this or it could be that. So you can't rule out either.
That.
Oh, it's great. It's great. I mean, it's a possible indicator of life on another planet that we can actually measure.
Of course, the sad thing is, if we do find life on Mars, and I shouldn't be saying sad, but I am, we still don't really know if it's something new or something that came from Earth, or whether life on Earth actually started on Mars, because Earth and Mars swap rocks all the time. They have been for billions of years.
That's right, and there's a lot of suggestion that life on Earth, some suggestion I should say, that life on Earth might have come originally from Mars. We're talking back in the old microbe stage. But the other question it raises, of course, is if they spot all this methane and they consider it's, they can't find any geological reason for it, and they do further investigations, whether that's a lander or a rover or whatever, to go down there, dig it up and measure some soil or something, and they find, hey, there are microbes here. The next big question is, well, there's a planet out there that's got life on it. Do we keep it in quarantine? How much should we mess with it? Do we want to go there and accidentally wipe it out or something? What should we do? Planetary protection, they call it. NASA's got a whole department that looks after this. They sterilize spacecraft that go off to other planets that could possibly carry Earth microbes with them. They can't eliminate every possible Earth microbe inside a spacecraft, but they do a pretty good job of wiping the whole things down and sterilizing them as much as possible. So, planetary protection, which is why, for instance, some spacecraft, when they send them out and go orbiting around planets and things, when they come to the end of their useful lifetime, thinking, in fact, this was Galileo.
Well, Galileo did that. Cassini's about to do it at the end of next year.
Yeah, they deliberately make them plunge into the atmosphere of the major planet as their final swan song, if you like, with the aim being that the entry velocity is so high that the spacecraft will just get vaporized, and any microbes that have happened to survive for 20 years in space will get vaporized along with it, rather than running the risk of just letting this thing drift around in orbit on its own, out of control, out of contact and everything.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. You're listening to SpaceTime. I'm Stuart Gary. A Japanese H-2B rocket has successfully blasted into orbit, carrying the HTV-6 cargo ship bound for the International Space Station. The 56-metre-tall H-2B was launched from the Tanegashima Space Center south of Tokyo, delivering 2.5 million pounds of thrust from its twin liquid hydrogen and liquid oxygen-fueled LE-7 main engines, assisted by 4 A3 strap-on solid rocket boosters.
15 seconds and counting.
Thermal
2, 1. The engines igniting, the solid rocket boosters, and liftoff. The H-2B has cleared the tower, the 6th HTV vehicle on its way to the International Space Station.
コウノトリ6号機を搭載した H2B ロケット6号機は平成28年12月9日午後10時26分47秒に
Good first stage performance. Again, those solid rocket boosters will fire for the first 1 minute 54 seconds into launch. The main engines of the first stage will continue to fire.
2016 Japan Standard Time 打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています After liftoff, the launch vehicle operation control was shifted from the blockhouse to the range control center. ロケットは現在初期飛行方位角を 108.5 度とし徐々に南東方向の太平洋上へ飛行しています The H-2B is now flying over the Pacific Ocean to the southeast with its initial flight angle of 108.5 degrees.
HTV continuing to fly over the Pacific Ocean.
ロケットは正常に飛行中であり
Should be coming up shortly on that solid rocket booster separation.
The H-2B is flying normally, and the Tanegashima station is tracking the launch vehicle very well. The first and second pairs of SRBAs were jettisoned.
So their confirmation that those solid rocket boosters have jettisoned.
The boosters were jettisoned some 2 minutes after launch, leaving the 2 core stage main engines to continue propelling the spacecraft for another 4 minutes until stage separation. The launch vehicle's upper stage then ignited its single LE-5B engine, powering the mission into orbit where the HTV-6 was deployed over the Pacific Ocean 15 minutes after launch. Once it reaches the space station, the orbiting outpost's robotic arm will maneuver the cargo ship to a docking port on the Earth-facing side of the station's Harmony module. The HTV-6 is carrying some 4,119 kilograms of fresh supplies. Included in the manifest is a specially designed pallet holding 6 lithium-ion high-powered batteries, which are lighter and more efficient than the space station's existing aging nickel-hydrogen batteries. 2 spacewalks have been scheduled to install the new batteries outside the space station's right-side S4 power truss on one of the 4 main solar array modules. Also aboard are new parts for the space station's carbon dioxide scrubber, as well as several tons of food, water and provisions, and 12 CubeSats, which will be launched into space from the Japanese Kaibo module over the next few months. Included among the CubeSats is NASA's 3-kilogram TechEdSat-5 spacecraft. It'll test the new exobraking system designed to slow down spacecraft re-entering Earth's atmosphere. Another CubeSat, this one developed by the University of Tokyo, will test the inflation of a torus-shaped aeroshell designed for deorbiting spacecraft. 2 other CubeSats, Freedom and Waseda-Sat-3, will each be testing new film-type deorbiting devices. Also in the manifest are 4 Lima 2 CubeSats designed to track global shipping traffic and collect weather data. Other CubeSats include the Aoba Velox-3, which will test a pulsed plasma thruster propulsion system, Italy's 2-pod CubeSat, which will try to launch a pair of smaller nano-satellites for Brazilian and American builders, the ITF-2 telecommunications CubeSat, which will be used by amateur radio operators, and the STAR-C CubeSat, which will attempt to extend a tether between 2 other CubeSats. Once the HTV-6 cargo ship leaves the orbital outpost, which at this stage is slated for January the 20th, it'll spend another week in orbit, unwinding and then testing an experimental 700-metre-long tether composed of strands of thin aluminium and stainless steel wire, which could provide a new method of removing space junk. This electrodynamic tether, as it's called, has a thin coating of lubricant which is designed to encourage electrical conductivity, which would then interact with the Earth's magnetic field to generate enough energy to change an object's orbit, allowing it to burn up in the atmosphere. If successful, the experiment could offer a new way to deorbit aging satellites, derelict rocket stages, and other space junk. We'll keep you informed. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.